Obviously, as you can realize, or as you will realize, I'm having the session a bit earlier compared to the actual time. Reason being that from the office, when I record, the quality is good, but from the house, my internet is unstable. So that's why I want to record it now. So if you're interested, let me know if we can have another session from 6:30, 6:30 or 6:40. Maybe just to discuss, even if we cannot go through the depth. If there are questions, related questions to what we have covered so far, we can have a session where we can interact. If possible, this evening or late, just let me know. Otherwise, maybe next time, I might record another video tomorrow. So last time, if you recall, I introduced the notion of topology because we're talking about Borel sets. And we know that Borel set is the Borel sigma algebra is the sigma algebra generated by open sets, right, for a particular topology. So for R, for the natural topology of R, you have the Borel sigma algebra over the real numbers, right? For an arbitrary topological space, you also have the corresponding Borel sigma algebra. And we are more interested in the Borel sigma algebra of the real number. That is the topology of R, the usual topology of R, which is defined by open intervals. Why? Because when we integrate, generally we integrate over Borel sets, right? I'm going to define what is a measure, because that's what we are going to cover now. And I will also explain why we need to define a measure, why we need a measure, and what is the implication of measure when it comes to integration. Because you integrate in respect to a measure. So you need to define what is a measure, right? And in measure theory, in fact, we generalize the notion of Riemann integrals, right? So the theory of integration is about generalizing Riemann integral, because it turns out that there are sets, right? If you use Riemann integral, there are integrals that are not defined, right? The integral that exists, obviously, the integral exists, but in the Riemann sense, it is not defined. When it comes, for instance, if you take the function, which is 1 on a rational point and 0 on irrational point, if you use a Riemann integral, it will not work. I mean, because you know that something is integrable if the Riemann sum converge to the same value. That will not be the case in here. It will not work. It will not be the case. So meaning that that function is not integrable in the sense of Riemann, but actually, if you generalize the notion of integral in the sense of Lebesgue, it will be integrable. So the integral will be defined, and that is thanks to the generalization, right? So we'll come back to this later on if you have enough time, because we really need to rush to cover this, because the LP spaces, as I said, are part of metric spaces, right? And they also have all the good properties that we are going to see later on, like this, LPs are all Banach spaces. Only L2 will be a Hilbert space, right? So everything that we'll be covering with topology, all that, you can do the same on the LP spaces as norm spaces, Banach spaces, and Hilbert spaces. So all the theory that we'll be developing later on will also be applicable to LP spaces. They are really special functions. And particularly for those of you who are interested in the financial mathematics, You cannot do financial mathematics without the LP spaces because you always use the LP spaces, right? Yeah. Even those who are interested in solving PDEs, particularly if you want to, because solving PDEs, there are two tendencies. You can study quantitatively, meaning numerical method to solve PDEs, obtaining the analytical solution. But you can also do what we call the qualitative analysis. And in the qualitative analysis, we use the LP spaces. Qualitative means you study the existence, the uniqueness of the solutions without knowing the solution, though. So in that case, you have to construct functional spaces. And the knowledge of those functional spaces are the subjects of functional analysis, because through functional analysis, you'll be able to know the framework in which you'll be looking for your solution, because the solution have to be in a certain space. And it's only in functional analysis that you'll be able to study those type of spaces. So is the solution in this type of space? If it's in this space, will the solution be regular? All these things are qualitative analysis, and they are embedded, or they are studied using the tools from functional analysis. So if you do functional analysis without knowing what are the LP spaces, and you are just told that, okay, LP is the set of functions that are whose modulus is whose modulus to the power of P is integrable. Yes, that's the definition, but you don't really understand what it means. You just say integrable. Which type of integral are you using? What is the theory behind that? All this will be uncovered. I mean, it will be covered. So they will be covered. You will not be able to see or to understand what it means. So that's what I say, that what we are doing currently is very, very important for your understanding and for the rest of your career, if you will be dealing with PDEs or functional spaces and the like. Really important. But personally, you have to study these things, right? Because I don't really see at the level of the institution here, if you don't talk about it, later on you will not be able, except you take a master class where they talk about the theory of integration or something like that, to give you a strong background. But already I'm giving you this information so that you know what you have to put in as a supplementary efforts to be able to level your ground, to level the knowledge of your background. Okay, so let me go back to the last slide, where we discussed. So this is what we did last time. We discussed about this structure of BR, and I will go straight to the definition of a measure. So I'm going to define a measure, because already what do we have? In order for us to define a measure, we need a measurable space, right? So let me recall. Let me make a short recall here. So we know already what is a sigma algebra. So we assume that we have a sigma algebra A, or F. It's a sigma algebra. Over a space X. or E or whatsoever. Let's take AX. Then this couple, that is X endowed with the sigma algebra, is called measurable. Measurable, meaning that you can put a measure or you can measure it. It's a measurable space. Measurable space. And any element of A, any element A in the sigma algebra is called a measurable set. A measurable set. Measurable set means that you can measure it, so you can apply a measure to it. So we have we have measurable set to indicate that you can compute. If f is a measure, you can compute f of A, or if mu is a measure, you can compute mu of A. Measurable space means you can define a measure so I will write the implication here. Let me make a remark here, right? That this is like a remark. Remark here. So if remark 1, let me put it 1 here. So for the first remark, XA measurable implies we can define the measure. Over X or A, over A, on A or over A, right? And the second one, 2 A measurable that is a measurable set implies that the measure, I will call that measure mu. Mu. So we can compute we can define mu A. We can define, we can compute, we can evaluate, right? Okay, this definition is already here. We can define or we can evaluate. We can evaluate. I think that would be the more appropriate. We can evaluate. We can compute or we can evaluate mu A. Measurable space, measurable set. Now the question is, what is a measure? What is a measure? What is a measure? So here we are going to define what is a measure. Okay, so we need a measurable space in order to define a measure, right? So what's a measure? A measure is nothing else than a map or a mapping from A to R plus. Of course, R plus including infinity, because the measure can take in the infinity. So a mapping mu, right? Because remember mu, this one, when you write it mu like this is the letter M in Greek, right? And when you spell measure, the first letter is M. So mu in general, we will use mu like M to represent a measure. So it's related to the meaning of measure. So measures start with the letter M, and this is M in Greek. So that's why in measure theory, you always see a mu being used to represent a measure. Obviously, it's not only mu. After mu, the next letter is nu, right? Mu is M and N is nu, like this. So like this, nu, right? So you have mu, you have nu, that can also be used as a measure, but you will not see F used as a measure. It doesn't, in fact, it's not in the jargon of measure theory. But you can still, if you say F is a measure, you can still use, but generally this is what the letter that you use to describe or to define a measure. Mu, you can say mu1, mu2, or whatsoever, or nu. Or you can also use lambda, because lambda would be the Lebesgue measure, right? So I'll put here in parentheses so we can use mu, nu, lambda. Those are the. So this is a notation, right? Notation for measure. So notation. Okay, let me leave it that way. So for the notation, you understand what I said. You can use mu, nu, or lambda, right? You can use mu, lambda. This is for the Lebesgue measure. You can use this, etc. So these are the various notions. I mean, not notion, but notations, right? For measures. All right. Okay. Now let me move to the definition. To the definition of the measure. As I said, it's a mapping from the set of measurable sets, that is your sigma algebra A, into R plus bar. R plus bar is from 0 to infinity included, so inclusive of 0 and infinity. That has the following properties. The measure of the empty set is 0, right? If the set is empty, you measure, the result is 0. Measure of the empty set is 0. Because that a measure, the probability, right? Probability function that you have been using is a measure. It's a particular measure. So we know that mu of the empty set, of the probability of the empty set is 0, because the impossible event's probability is 0. So if you measure the chance for that event to occur is 0, right? Now the measure of two disjoint set of the union of two disjoint set is the sum of the measures of the two sets. So if you have a countable number of measures or of sets which are mutually exclusive, meaning they are disjoint, mutually exclusive generally for event, which are mutually disjoint for two different sets, A sub I, A sub j. A sub I intersection A sub j is empty. So if you have a collection of such finite or countable the measure of the union of all this collection will be equal to the sum, or the infinite sum, if you have many, of mu A sub I. So these are the two properties. Two, yeah, the first one, the second one, and the fact that it's positive, right? Positive. The positivity is the first property. Mu empty set 0, and then additivity. Subadditivity now is if the sets are not disjoint. That is, if I compute the measure of A union B, where A and B are arbitrary, this measure will be less than or equal to the measure of the sum. It will be less than or equal. That is, you call it the subadditivity property. But it will be additive, that is equal, when the two sets are disjoint. So we are going to define this in our slide. All right. So definition. A map or mapping mu defined from A So given a measurable set, a measurable space, X given. Okay, a mapping now from this A into R. I don't want to, I just put R here because I want to use the positivity as a property, right? Or I can just put it there. It's called a measure if first property, it is positive, let me take a bar here to indicate that positive infinity and negative infinity are there. It's positive. Positive. And you can also take the value positive infinity, because if I write the bar here, remember, the bar is what? It's the closure, right? So since the interval, the endpoints of of R at interval, you have negative infinity, positive infinity. Now, if you take the closure, it will include infinity, positive infinity. Now, because it's positive here, you can also take infinity, right? So I'll write it here to make it clear that mu, when I write like this, it means that at each point x, right? Mu, this is a function. I can say mu x here will belong to, oh sorry, mu a or mu whatever is here, whatever you call x. That's to be rigorous, right? Mu a, that is to be rigorous in our, so that is in the interval 0, infinity or positive infinity, the same thing like that, right? For any a in the signal algebra. So that's what it needs to be positive. Or in some other definition, this interval would just be replaced here. But you have to bear in mind that it takes its value here. That's why I'm stressing on it as a property, right? It takes its value in the interval 0, infinity. And it can be infinity, right? Because we are dealing in the closure of R, or positive, right? Closure of R. And measure is always positive. The measure cannot be negative. Okay, now the second property, which in some texts is the first, we have mu of the empty set, right? We know that the empty set is an element of the sigma algebra, is 0. But nothing is said about mu of x, which is the x is the entire set, right? Or the entire space, if you want, this x. Nothing is said, but for a probability mu of x, in probability x will be replaced with omega. Mu of the set itself, the entire set or the space, will be reduced to, will be equal to 1. Right. So in the definition of measure, we don't say anything about that. We only give the value of mu of the empty set. Okay, now the last here. So if we take a countable for any collection of countable set, any collection of countable set, of countable set. The sets are not countable, but it's the collection that is countable, right? For any countable collection, right? Because if you say for any collection of finite set, I replace countable with finite, you have the impression that the set are finite, whereas it's the collection that is. So let me change this. So for any countable collection, for any countable collection, collection of disjoint set. A1, A2, up to infinity if they are countable, if it's finite, which is also finite countable, you stop there. But if they are infinitely many, you continue, right? disjoint. Then mu of the union AI is equal to the sum. You see that here we have equality when they are disjoint, right? Now we take all the sum from 1 to infinity. So this is a series, in fact, if they are countably many. So this is what we have. Okay, this is what we call additivity. Additivity. Now, if the sets are not disjoint, therefore this becomes less than or equal, and this will be called subadditivity, right? So what I mean here is that if the sets are not disjoint, now this will become less than or equal. And for this less than or equal, this will be subadditivity. Subadditivity. All right, so we have two definitions there. The case where the collection is disjoint, pairwise disjoint, that is two arbitrary sets are disjoint. But if you don't mention that, this will be what you'll be using the definition be subadditive. And that's exactly the same that you have in probability, right? Because what we are doing is something that you know from probability. You know that if you have two mutually exclusive events, the probability of the union will just be the sum. But if they are not, P A union B in probability is PA plus PB minus P what? A union B, intersection B. But you can see that this is less than the sum. Now you see that probability of the union is less than or equal to that. Now if they are disjoint, you have equality, and this will not be there. So you see that this will be equal to that. So this information about the set being disjoint is what gives you equality. But if you don't specify that information, you use less than or equal. And that property will be called subadditivity. Right. Okay, so this is worth mentioning. So that what you know from probability will still hold here, right? Because this is more general than the definition that we have in probability. So I already specified here more measurable sets, element of A, and this is a measurable space. Right. Now, if we define a measure on A, now the triplet, so you see where I'm going, eh? The triplet, now we can define what we call a measure space. The triplet will be called a measure space. So I will add that information here. In the case we have a measure on so in the case we define a measure over A, the triplet X the sigma algebra and mu like this is called a measure space. Measure space. So if you replace mu with a probability, you know that this is called probability space. So you replace measure with probability. So if mu is a probability, the triple becomes a probability space. Okay, so far things are, I'm just trying to make the correlation between this definition and what you already know from probability. So this is a measure space if mu is a measure. If mu of A is equal to 1, it becomes a probability, right? And then you call it a probability space. So let me give another definition. Now, the space X itself, or the set X, is called sigma finite. X is sigma finite if remember the terminology sigma. When you say sigma, it means that you have a countable union. Never forget this. When you say sigma algebra, remember we say sigma algebra came from the fact that this countable union is an element of the sigma algebra. That's where the sigma comes from, countable union. So now if you say that X is sigma finite, so the sigma first comes from the fact that you can write this X as a countable union. That's the sigma. And then finite comes from the fact that mu of X itself, I mean not mu of X, but mu of each of the element there has to be finite. So if sigma finite, if there is or there exists a countable family or a sequence, if you want, in A. So I write sub, I don't say element, right? Because this is a sequence. Each element is there. So if I take the entire collection, it's a subset of that, right? Such that X is the union of Xi So this is the sigma I mentioned. Finite each one. And mu of xi is finite for any I. So this is sigma and this is finite. Sigma finite. So let me write that here. So this is sigma and this is finite. Okay, so we have a. I would just add another important definition that is usually used. A set E element of, that is a measurable set with a property that mu of E is 0 . You see that this is a set except the empty set, right? This is a set which is not the empty set, right? Any other set except the empty set that has this property is called a negligible set. It's negligible because it has element, it's not empty, but its measure is 0, so you can neglect it. It's called a negligible set or a null set. A null set also known as negligible. Okay, so from here, where do we go? I need to give you some examples because if I just leave you from here without giving you examples of measure, right? Then your appetite will not be quenched, right? You might have nightmare during the night. So I don't want you to have nightmares, right? Because you'll be sleeping with an unquenched thirst, right? You go and sleep but with an unquenched thirst. Oh, I'm not satisfied. There's something is pending there. There's a thirst that has not been quenched. So, okay, example. I will give you an example. And that would be the first example. And there is a motivation, right? Why I'm giving that example. Okay, example. Now, if I take x equal to r, so if I take x equal to r in our A, we take the Borel. So we know that interval, for instance, of this form in VR. Now we can define mu from VR into so if I take an element here of that form, of course, it can even be opened, right? It's not necessarily a closed interval. It can be open here, closed there, for any element there, anyway, any element there, right? Now you will see that here we can take infinity. So if I take, okay, let me just take this, an arbitrary element here. We know already all the forms, the structure, we know the structure of that. So if I take an element here, I associate mu A, which is the length of A. So this is a measure. Over or on BR here on the Borel sigma algebra. It's a measure. Why? Okay, if we know that the empty set is there and mu, if I have an empty set, what is the length of an empty set? Is 0. Let's take an example, right? Let me take an example. The length is always positive. We know that the length is always positive. mu is greater than or equal to 0. It can also take infinity, right? You see that. Length is always positive. Length is always positive. And then if you take, let's say the interval a positive infinity, right? You know that the length will be infinity because we take infinity minus, right? The interval a b, the length of a b is b minus a. I know that the length. Okay, so you will take in the value infinity if one of the endpoints here is infinity, right? Let's say this is infinity, then you take infinity minus here. Infinity, if you have infinity here, infinity minus whatever value is there will be infinity. Now, if you have negative infinity here, and whatever number you take there, it will be the number minus negative infinity, that will still be positive infinity. So we see that it can be 0 or infinity because of the structure of dr, right? You can see. So it takes its value there. I will not stress on that anymore, so I will continue. Now, how do we prove that the measure of the empty set is 0? Now, if I take this, if I take this set, if I take the interval I or A, because they are all intervals, if I take A, this interval, open at A, close at A. Sorry, open and open there. If I take this open interval from A to A, we know that open interval are there. So if I take A equal to A or A equal to B, I have this, and this is the empty set, right? Obviously, A is an element of R. Of course, it's an element of R. It's an element of R. And it's a finite. I can take it finite and arbitrary. So if I have that, this is what I have. And we can see that mu of A, which is the measure of that, it will be A minus A, right? So I take this point minus that point. So B minus A, BB equal to A is A minus A, it gives you 0. Right. That is mu of the empty set is 0 when we use length of interval. That's what we get. So it is compatible or consistent Okay, now if I take a countable union, okay, countable union, but make sure that they are disjoint. Countable union, and we make sure that the elements are disjoint. So if A1, A2 is a collection of element of BR. Okay, since they are in BR, they are intervals. If they are intervals, we can arrange this of disjoint, right? Of disjoint of the countable family of disjoint element. Disjoint element. Disjoint. Element of BR. Since these are intervals and they are disjoint, we can rearrange in such a way that we have an increasing, no, not increasing, we can sort them out, right? We can sort them out, meaning that we can write one before the next and so forth. So we can arrange in such a way that here we have an increasing sequence, right? We can take this sequence as an increasing, meaning that this interval will come before that one and so forth. So if that is the case, if we can sort, if we try to sort, if we sort this interval, so it means that A1, we can write A1 this way, for instance. And because they're disjoint, A2 might start somewhere there. There will be an empty space between them. They will not overlap, right? They will not overlap. So this, we can always do that because they are disjoint, right? So we can do that. So we can do that. Here we have, for instance, A1. Even if originally the sequence is not like that, then we can still rearrange because it's an interval. Here we have A1, B1. And then the next one will be somewhere here. You sort them out in such a way that this one will rename it A1 and the next one will rename it. So after a renaming, right, process, you can always sort them out in such a way that we have something like this. And so forth. This will be like a certain N, AN, and so forth. It continues forever. So you can always group them. But because they are disjoint, they will never touch each other, right? So we have this gap between them. Good. Now, if we take such a sequence, we rearrange, and rename like that, they are disjoint. So now, what will be the union? How will I write the union? Mu of the union, if I take this union, it will be this, union that, union that, union that. Now, the measure of all this so observe that I cannot write this union as a single component. I can't do that. I will not be able to do that. So you see that it will be the sum because this is the union. The union is all this. Now, if I want to measure this length and that length, and then you see that I will add them up. So it will give us this length, B minus A, B1 minus A1, plus B2 minus A2, B3 minus A3, B4 minus A4. Here you have AN, BN, Bn minus An plus, and it will continue forever. And what is this? This is mu A1, mu A2, mu An, and forever. So we'll be adding all of them, which is actually this infinite sum. If you have infinitely many, all right. But can we do better than this? Can we obtain a better result? Yes, we can always. We can always do that. Or I can give extra problems. But it's good. Yeah, it's good to construct. Um, okay, so I will give another. I will give a problem that we'll quickly try to solve using the properties of the sigma algebra. I mean the sigma algebra. Uh, okay, let me quickly give you a proposition or a property. In fact, that's something you know from probability. Let me quickly write this one. That's a result. I will property. I will just give a single property which you know already. Okay, in terms of example, I will add more example next time, right? There are many examples. There are many. This is the first one that came to our mind. There are many others. We will construct. There are so many. But what I want us to do now, we need to, if you want to apply these properties, right? This is from this definition. We can show that if A is a subset of B, right? Mu A is less than or equal to mu B. I think that's something that was done in probability. Can we quickly do that, and then we'll do another problem, and that will be the end. We'll stop there. So, property. If then mu A is less than or equal to mu B. Obviously, they will be equal if A is equal to B, right? But it's a subset, so it will be less than or equal. If it is a subset without the inclusion, right, then it will be strictly less than. Okay, in order for us to do this, we'll use the last property, right? This one, this last property. If you use this last property, then we are done. We rearrange because A is a subset of B. We can construct this. Let us use. So A is a subset of B. We can write it this way. We can write that. This is, for instance, our B, and inside here we have our A. So this is A, and this is B. So we can write B. I can write B as the union. So I can write B as the union of two. Union as a disjoint union of A and this part. And what is this? This is B intersection A complement. So I can write that B is equal to A union B minus A, which is B intersection A complement. A complement is everything outside. Then if I take the intersection with B, it gives me this outer part. And that outer part is this. So this red, this shaded part is B intersection A complement or prime of a complement is generally like that. So A complement is everything outside, but if I take intersection with B, it means that it has to be part of B. But it's not in A. So it's this one. Now if I take A union this, it gives me B. So we see that A and this are disjoint because an element here in A cannot be in the intersection with A complement, because remember an element here is not in A. So the intersection with A will be the empty set. Right. So you can convince yourself by writing this intersection that. So if you write A intersection this set, if we call it E, if we call this set E, A intersection E is equal to A intersection B intersection A complement. So we know that intersection is a commutative law. I can change these two positions. Therefore, this will be A intersection A complement, like that, intersection B, and this is the empty set. So that will be empty set intersection with B, which is still the empty set. So it's empty. All right. Since they are empty, we can then write, we use property 3, that mu B is equal to mu. They are empty, so I can just apply to this one and just split. That will be A plus mu B intersection A complement. And we know that the measure is positive, right? We know that the measure is positive. Or 0. So if I add a number that is positive to 0 to another number to get the next one, it means that this is greater than that one. And because it's greater than or equal to 0, this implies that mu B greater than or equal to mu A. Or if you want, if you don't want to write it directly, you can just say that mu A is equal to mu B minus this, which I call mu A, mu E, this one, mu E. But this is less than or equal to mu B. Why? Because this is positive. So, okay, shall we stop here? Okay, let me give you a homework. Before we part. Homework. Let X A mu be a measure space. Show that for any AB, A, B, in the sigma algebra, we have the equality. Mu A union B plus mu A intersection B equal to mu A plus mu B. All right, so what should you do? You first assume the case where, because remember mu takes its value in the interval 0, infinity, including infinity. You can first take the case where mu of A or mu of B is infinity, right? When you say or, it means that one can be infinity, the other one is not, or both can be, right? You show that this will be true in that case. And the case where you really need to apply the properties when both A and B are finite. That's mu A finite, mu B finite. That's where you really need to go into the detail. Otherwise, when A, the mu of A or the other one is infinity, you agree with me that you have identity here, right? Because if mu of A or mu of B is infinity, this intersection, this one, will be contained in one of them, or either of them. The one with mu is infinity. No, is that even correct what I'm saying? Okay, you can even use this one. The one with infinity will be contained in the union, right? And we know that the one with infinity, its mu will be less. Okay, let me quickly say it here. What I'm saying is that distinguish this is a hint, distinguish or use distinguish between first case A, mu A, is infinity or, because this or can be exclusive or inclusive, doesn't matter. Both can be, but okay. And then the second case, mu A. Now you see that here I'm saying and both have to be finite. So mu A finite, mu B finite, both finite. That's where you go into the detail. But you can see that this one, the first case, is trivial. This case is trivial. Why am I saying that it's trivial? You can see that if either mu A or mu B is infinity, the left-hand side is infinity. Why is it infinity? A or B will be contained in the union. So meaning that this mu A, mu B will be less than or equal to mu of the union, which is infinity. Okay, that one is also correct. Right, so this implies that mu A or, right, because I say or. Now, the case is, How did I put all here? Okay, it doesn't matter. You see that it will be less than or equal to what? Mu of the union. You see, I can replace this by A or B, right? But if this is infinity, any value that is greater than infinity is infinity, right? Okay, so if okay, I'll write here. In fact, both A and B. So this is N. Or A, comma, both. Now I will have mu A, N. So it will be both. Of course, because it is all, I will select the one. So I will say all here. Okay, these two are. So I will select the one. So among these two, I will use the one that is finite. I don't need both to be finite. It is enough for one of them, and that one is the one that I will use in this inequality. So if it is this one, if it's mu A, I will just keep this. And now if this is infinity, so mu of the union is greater than infinity, meaning that it is infinity. Right? So it will mean that mu of the union is infinity. So if I add the intersection to infinity, it's still infinity. And the sum is still infinity, so there will be equality, right? That's what I mean. Right? Because this will be infinity from the union, whatever I will be adding, because this is positive. Any positive value that I add to infinity from here, this is infinity. We know already that one of them is infinity, so if I add a positive term to an infinity, it's also infinity. So the two will be equal. So that's why I'm saying that this is trivial, because we have this. Now for this one, we now need to specify the case where both mu A is finite and mu B is finite. Therefore, you have to write A union B and A intersection B in terms of what? In terms of the complements, right? I mean, the hint for this one, in the second case here, in the second case, right? So this is the hint. Right? A union B comma A comma B in terms of A intersection B, because you need to have the intersection A intersection B, so you have to express these three in terms of that. And or where applicable, right? Where applicable. A minus B, B minus A. Okay, that is it. So you need to write all of them in terms of the intersection, right? Like, and also in terms of A minus B and B minus A. But you cannot write A in terms of B minus A, right? That's why I say where applicable. So I can only write A in terms of A minus B. because I cannot write in terms of b. I cannot remove b from a and expect a to be equal to such something. But we know that if I write a like this, that is b, this is a, that is b, right? I can always write a in terms of the intersection if it's non-empty. I can also write b in terms of the intersection. But you can see that this b, this part will not be a, it will be b minus a here. And this one will be a minus b. So where applicable, so you cannot write for each one in terms of these two. Some will be, like the union can be written in terms of the two, but not A. A cannot be written in terms of this, and B cannot be written in terms of that. So for A, it will only be this one, for B, it will only be that, but for the intersection, it will be both. So once you write that in terms of, you apply the property of the measure, and you should be able to get this result. So I assume this is done. So that is the homework. Write it yourself. Thank you for your kind attention. We are stopping here. God bless you, and see you tomorrow, because I will record another one tomorrow. And please read them and try to do the problem. Try to understand all these things. They are really important. Okay, thank you so much. God bless you. Bye-bye.